Hello, this is Professor Keene. In my previous lecture, I began discussing Newton's propositions and theorems in Book 3 of his Principia. Remember that in these propositions, what he is doing is he is developing, finally, his universal law of gravitation. In the first two propositions, he demonstrated that the forces acting on the moons of Jupiter are inverse square law forces. That is, they get weaker as 1 over r squared as one gets farther and farther from Jupiter. He also demonstrated then in proposition 2 that the forces acting on the planets that are going around the sun are direct. They experience a force directed toward the sun, and the more distant planets experience a weaker force, and that in particular the force is a 1 over r squared kind of force. He invoked the various phenomena of Book 3 and also the propositions that he developed earlier back in Book 1. In this lecture, I want to talk about his proposition 3, or theorem 3, which is at the top of the page here. So let me just articulate it here, and then I'll explain the significance of it. First of all, he says that the force by which the moon, by that we mean Earth's moon, the force by which the moon is retained in its orbit tends to the Earth and is reciprocally as the square of the distance of its place from Earth's center. Okay, so what is he saying here, and how does he prove it? So let me dip my pen in the dark ink here. Okay, so the first point that he's making, point number 1, in this proposition, is that the Earth's moon feels a force directed toward the Earth. And I'll go through the proof of this right away. This is a fairly straightforward proof. Well, he knows this by phenomenon 4 and proposition 2 of Book 1. Remember what these are. Proposition 4 was in phenomenon 4, he noted that the Earth, when considering its orbit around the Earth, by a line drawn from the Earth to the moon, that radius line sweeps out equal areas in equal times. So that is phenomenon 4. And then, once again, he's invoking proposition 2 of Book 1 that says, if equal areas are swept out in equal times by a body going around a central point, then there must be a force, a centripetal force acting on that body. So there we have it. The moon feels a force directed toward the Earth. Point 1. Point 2 is that this force is reciprocally as a square of the distance of its place from the Earth's center. In other words, the force pulling on the moon, on Earth's moon, is proportional to 1 over its distance from the Earth squared. That is, it's an inverse square force. Okay? Now, how does he prove this? The proof here is not nearly so simple as the proof that the forces acting on Jupiter's moons were 1 over r squared forces, and the forces acting on the planets as they orbit the sun are 1 over r squared forces. Why not? So this is, he cannot use the fact that they obey Kepler's third law. He cannot invoke Kepler's third law to justify a 1 over r squared force. Why not? Why can't he use Kepler's third law like he did in proving a 1 over r squared force for Jupiter's moons, for Saturn's moons, and for the planets? Well, remember what Kepler's third law says and how it was invoked in those previous proofs. They said if you compare any two moons of Jupiter, like Jupiter's first and third moon, for example, if the periods go as the radii of orbit to the 3/2 power, then the forces must be 1 over r squared forces. And likewise with the planets, if you compare the orbits of any two planets around the sun, their periods of orbits, so for example, the period of orbit of Mars and Jupiter, and then you compare their radial distances from the sun, if the periods go as the radial distances to the 3/2 power, then the force gets weaker as 1 over r squared. Why can't he use that here? Well, simple. The Earth only has one moon. You cannot compare the orbit of one moon of Earth to the orbit of another moon of the Earth. Of course, nowadays one could do that using multiple satellites, artificial satellites going around the Earth. Newton did not have that luxury. There was one moon, so he could not use Kepler's third law to justify a 1 over r squared force. So how does he do this? Well, he invokes something that we did not study. He mentions that, so he can't use this, but what he can use is the fact that the apogees of the moon are stationary. I'm not going to be able to explain this in a way that will completely satisfy you. Let me just state what the apogees are. So if you have the Earth right here, this is the Earth, and you have the moon going around the Earth, the moon does not go in a perfectly circular orbit. It goes in an ellipse, and the apogee is its point of farthest distance from the Earth. That comes from Greek root apo, meaning away from, and geo, meaning earth. So it's farthest away from the earth. By the way, this point would be the perigee, the closest point to the earth. But the point he's making is that this apogee, as the moon goes around the earth, it returns to the same point in space. So if you're looking at this from the earth, looking up at the moon when it's at its farthest point, and you notice it's happening in front of a certain set of stars or a certain constellation, the apogee is to a good approximation always happening in front of the same constellation. That is, it is not precessing. So the apogee is stationary, as opposed to a precessing apogee would be if its apogee happens at one point here, and then maybe a month later the apogee is happening over here, and then a month later the apogee is happening over here, and a month later the apogee is happening over here. That would be a precession of the apogees. Now, why does this matter? Well, because if there's a stationary or very nearly stationary apogee, that implies that the force holding it in orbit is a 1/r² force. I did not prove that to you, I'm simply stating that. Newton goes through a proof of this in a different chapter of his Principia. If, on the other hand, the apogees were precessing, then the force would go as 1/r to some other power, x, maybe 1/r to the 2.1 or 2.8 or something like that. So in the paragraph that is right after this proposition 3, theorem 3, he explains that the force pulling on the moon must be a 1/r² force to a good approximation. And in fact, it deviates a little bit from 1/r², but he argues that is because not only is the Earth pulling on it, but the sun's pulling on it a little bit too, and he tries to make a correction for that. So he gives here a plausible argument that the force acting on the moon is proportional to 1/r². I don't think it's nearly as tight of a proof as his other proofs, but nonetheless, he has to use more extreme measures, you might say, in trying to argue for a 1/r² force acting on the moon. Okay, let's put that behind us. I'm going to introduce you to proposition 4, theorem 4, tell you the basic idea, and then I'll go through that proof in the next lecture. So let me import that. Here's proposition 4, theorem 4. I'll read it for you, and then I'll make a few comments and then discuss this in more detail in the next lecture. Because this one is going to take a bit more time, but this is really the most fantastic proposition that Newton comes up with. And this is where the story of Newton comparing the orbit of the moon to an apple falling on his head isn't so far from the truth. Okay, so here we are, proposition 4, theorem 4. That the moon gravitates toward the Earth, and by the force of gravity is continually drawn off from a rectilinear motion and retained in its orbit. Okay, so the moon goes toward the Earth and is maintained in its orbit by that force. And in the paragraph right after this, he is going to argue that, so he will argue that the same force which holds the moon in its orbit, this 1/r² kind of force that he developed in proposition 3, that force also causes terrestrial objects to fall. Terrestrial objects like rocks and apples to fall. That is what he's going to argue, and I think I will stop there and go into this in my next lecture.